So, in the last session, we've been talking about different ways of expressing base elements of a finitely generated free Abelian group. And also, we established a sufficient and necessary and sufficient condition for a subset of a group to be a base element. And also, we defined the direct sum. So let us take a look at some subgroups of a finitely generated Abelian groups, free Abelian groups. So let us say C cross C. This is a finitely generated free Abelian groups. We have already seen this, and one of the base element, one of the bases is C1 0 0 1, and I'm going to take another subgroup of this. Let us take 2C 3C. Then the base element of this, a basis for this subgroup is going to be, let us say, 2 comma 0 and 0 comma 3. So we know that this is not the only one basis for this finitely generated free Abelian groups, and so is we can find different base elements. Our idea is to find the base element for this parent group and subgroup with a nice relationship. For example, here, if we can take another basis like this, 2 comma 3 1 comma 2. This is a basis. One way to check it's a basis is that, if you take the determinant of this, that should be equal to the value of the determinant of this is equal to the value of the determinant of this. For example, 1 0 0 1 is equal to 1, and this one is also going to be, you can calculate, this is also going to be 1. And that is one way of verifying these two sets are the base elements of. The reason why I picked this base element is because we can find another base element, say 2 commas, it's 2 comma 3 and 6 comma 12. This, if you take this one as A and this one A1, this is as A2, this is going to be 1A1, 6A2. So there is a nice relation between these two base elements. And of course, once you find a base element like this, we can conclude that a subgroup of a finitely generated free Abelian group is also a finitely generated Abelian group with rank less than or equal to the rank of this. In here, the ranks are equal. This is equal to 2 and this is also equal to 2. The rank is the number of base elements. So that is an important result in the finitely generated free groups, and that is what we are going to discuss today. So we are going to establish a very nice relationship between the base elements of a finitely generated free group, Abelian group, with its base elements of its subgroup. So the theorem is like this, the result. Let H be a subgroup of an abelian group G with the finite rank n, then there exists a basis, let us say a1 dash dash an of G and integers d1 dash dash dr such that d1 divides d2 divides dash dash dr and d1 a1 d2 a2 dash dash dr ar forms a basis for H where R is less than or equal to N. So in the previous example, both R and N are same, which is 2, and D1 was 1, D2 was 6. See, this is a very, very popular result in finitely generated Abelian groups, free Abelian groups. So there are several proofs for this theorem. So the proof which we are going to do today is based on induction. So what we do is we'll show that the result is true for a group with rank equal to 1, an abelian group with rank is equal to 1. Then we'll show that, or we'll assume that the result is true for n minus 1, a group with rank n minus 1, and show that it is true for n. So let us begin proving the first step. The first step, see, when n is equal to 1, the group is isomorphic to G. Because it is a finite abelian group with a finite rank, not finite abelian group, it's an abelian, finitely generated abelian group with a finite rank. So it is always, see, if the rank is n, G is isomorphic to the direct product of C's n times. Always. And we already established this result. So here when n is equal to 1, G is isomorphic to Z. So that means every subgroup H is isomorphic to either 0 or MC for some integer m, because these are the only two types of subgroups of Z. So the result is trivially true if H is equal to 0. Because the rank of this is 0 and there is no D1. So there is nothing to prove here. So let H is equal to MC. In this case also the result is true. The result is true because the rank of subgroup is 1 and C is generated by 1 and MC is generated by M. And that means D1 is equal to 1 and D2 is equal to M. Alright, just D1 is equal to M. No D2s. Because the rank is 1. So the theorem, the result is true when n is equal to 1. So let us prove the second step. The way to prove the second step is that we are going to assume that the result is true for an Abelian group with rank n-1. So we need to get a group with rank n-1. So let us start with a group with n, and that is G, and try to express this G as a direct sum of two smaller groups. In this case, what we are going to do is we are going to find a group of rank 1, that is G1, and the rank n-1. And similarly, we are going to split the subgroup as H1 as H2. We are going to split it. I am going to explain how we are going to split this one. Here also, the rank of H1 is 1 and rank of H2 is, the rank of H-1. So this is going to be, and also it's going to be like H1 is a subgroup of G1 and H2 is a subgroup of G2. So this part is the assumption. G2 is a group with rank n-1. So the result is true for H2. So we have a basis for G2 that satisfies this condition. And what we do is we'll include H1 to this mix and get H and G. So that is the idea. So let us start with let A1 comma dash dash AN be a base. Let us take it as B1 because our end result is going to be A1s. So be a basis for G. This is possible because G is an Abelian group with finite rank n. So n elements, n linearly independent elements generates G. And H is a subgroup of G. That implies every element of H can be expressed as H is equal to K1B1 plus K2B2 plus dash dash KNBN. Some of them may be zeros, but it cannot be more than this. It has to be less than this. because it is always coming from a subgroup. So what I'm going to do here is, instead of K1, I'm going to write it as D1, just for the first one. Then I'm going to rewrite this one as D1 of B1 plus L2 B2 plus dash dash Ln Bn plus, we are taking D1 out. So it could be a multiple of K2, could be a multiple of D1, but if not, there is a remainder, and that is R2. R2 B2 plus dash 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 Rn Bn. So we can write any element of H like this. In here, we probably will not have this part for some H, not all H, but some H. This part may not be there. I'll give you an example here. Let us take Z cross Z and 2Z times 3Z. Okay, so this actually we can write it as one way of writing. I'm going to get two elements here. For example, one is 4 comma 6. Another one is 4 comma 9. This is one of the H1. This is other H1. This I can write it as 4 times 1 comma 3. And here you can write 4 comma 1 comma 3. Sorry, not 4. This actually, let us assume that this is 12. Sorry. So this we can write it as minus 0 comma 3. The first element I'm taking as 4 comma 12. Second element I'm writing as 4 comma 9. So this is for here. In this case, the second part is 0. This is our first part. And there is no second part, actually that is 0. Here there are two components. This is our first part and this is our second part. Both belongs to this subgroup. So in H, there are two different types of elements. One without a second part and the one with both parts. Let us call this one as A. Okay? Or let us not call this one A, but we'll call when R2 B2 plus dash 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 Rn Bn is equal to 0. This is not always true for every H, only for some H. Then H is equal to D1 B1 plus L2 B2 plus dash dash Ln Bn, and that we'll call as X. So elements that can be expressed as in A are in this form. In this case, if you expand this one, what happens? Every or the coefficient of every base element in every base element of an element in H expressed as in A, every element, the coefficient of every element of base elements expressed as in A forms a subgroup of C. They are all integers. For example, here what we did is 4, 12. If we don't have any second part, this has to be a multiple of this. So, sorry, there is a common factor here. For example, another one is 2 comma 18. Or 2 comma 6. So you can write 2 outside, 1 comma 3. Here 4 comma 1 comma 3. So these are the coefficients. These always form a subgroup of C. Let us say we call that subgroup of S of C. So the coefficient of every base element of an element from H expressed in this form forms a subgroup S of C. And if it is a subgroup of C, then S is equal to either 0 or S is equal to some D1 C. Okay? But if S is equal to 0, what does that mean? That means this part is 0. Then that means H is generated by B2 dash Bn. There is in the second part you don't have B1. There are only n minus 1 element. And that means is generated by, that means as H is a subgroup of G prime, which is generated by B1 dash Bn. So by assumption, the result is trivially. So we are not going to assume it is 0. So that means S is equal to a group generated by an integer D1. Now let A1 is equal to B1 plus L2 B2 plus dash dash Ln Bn such that dA1 A1 belongs to H. We are expressing an element of H as in A, then we are taking this D1 as a common factor that is the lowest integer that appears as a coefficient of the base elements. Then you take any elements that is expressed like this, and that is A1. So that implies A1 comma dash dash A1 comma B2 comma dash dash Bn forms another basis for G. B1 dash dash Bn is a basis for G. I am replacing B1 with A1. That is possible because of our earlier result. If x1 dash dash xn is a basis, then we can replace xi with xi plus txj for some non-zero integer t. So we already established the result. So this can be another basis for G. Now we are almost here. We are ready to split both G1 and both H and G. G is equal to A1, or G1 is equal to A1, and G2 is equal to the group generated by B2 dash dash Bn. Similarly, H1 is generated by D1 A1. See, H1 D1 is in H, and D1 is a common factor, and that is the generator of this subgroup. And H2 is going to be H intersection G2, meaning the elements of H that are generated only by these n-1 elements, that is this part. So this part goes to H2 and this part goes to H1, and there is no common element other than the 0. So if you define like this, what we have is G is equal to G1 direct sum G2 and H equal to H1 direct sum H2. See, in these two there are no common element other than 0 because there is no B1 here. Okay, similarly here. So that implies H2 is a subgroup of G2 and G2 is of rank n-1, and that implies the result is true for G2 and H2. That means there exists a basis A2-An and D2-Dr such that D2 divides D3 dash dash dr and D2 A2 comma dash dash dr ar forms a basis for H2. We are almost there. Now, because of this relationship, we can say that G is generated by or to be precise, a basis, or you can say, for G2, the basis is this. Sorry, the G2, the basis is this. This is a basis for G2. That combines with the base element of G1, which is A1, forms a basis for G. So A1 comma dash dash AN forms a basis for G, and D1 A1 comma D2 A2 dash dash DR AR forms a basis for H. Because H1 is generated by D1 A1. H2 by assumption is generated by D2 A2 dash dash DR AR. So when you combine these two together, H is generated by this. Now the only thing which remains to prove is D1 should divide D2. D2 divides D3 etc. dr because of the assumption. But we still have to prove that D1 divides D2. So D1 A1 plus D2 A2 belongs to H. Why? Because these are base elements. And this is in this form because this contains a B1, because A1 contains B1. A1 contains B1. If an element in H contains B1, it is in this form. And that implies D2 belongs to S. Because if you express this as in A, every coefficient of the base elements belongs to S. Because that is how we are forming the S. Every base element of an element. So that implies D2 belongs to S and S is generated by D1. That means D1 divides D2. And that is the proof of the result. We'll take a look at some examples. So the first example we are going to take a look at is G is equal to C and H is equal to H is equal to 2C times 5Z. See, one set of base elements for Z is 1 0 0 1, and one set of base element for H is 2 0 comma 0 5. So if you take any base element, any other base element of G, that should have the same determinant value of the base element of this. The determinant value of the base element of this means you are forming a determinant by elements from the bases like this, and that is 1. So if you take any other base elements, the value of the determinant has to be 1. And we already, the way we proved the theorem is we are splitting H into 2 parts, one with the element from 2 and the other without an element from 2. So the first base element of this will be always 2, 5. 2, 5. And we need to find out the other base elements so that the determinant is equal to 1. So that is 2, 5, AB should be 1. The only one way of getting this one is 2, 5, 1, 3 is equal to 1. So definitely 2, 5, 1, 3 is a basis for C cross C. Now the determinant value of H is 10. Determinant of 2005 is 10. So every base element should have 10 as the determinant value, and it has to be a multiples of this, meaning we need to find out D1 and D2 such that D1 divides D2 and 2D1, 5D1, D2, 3D2 is equal to 10. So this will be a factor of D1. D1, so D1, that means D1 and D2 are factors of 10 and D1 divides D2, and that implies, and both of them are integers, that means D1 is equal to 1 and D2 is equal to 5, D2 is equal to 10. So that means the base element of 2Z 5C is 2, 5, 10, 30 is a basis for 2C 5C. We'll do one more example. Here I am going to take it a little more complicated than the previous one. C cross C and H is equal to 2C cross 5C cross 7C. So we are going to the approach is going to be the same. The determinant value of the base element of G is here also, it is 1, because 1 0 0 0 1 0 0 0 1. So the determinant value of this is, so definitely any base element, if you take the determinant value of any base element of G, has to be 1, and it should start with the, so this is going to be 2 5 7, and you should keep on decreasing this value, because you are trying to eliminate we are trying to eliminate base elements from when you go from the top to bottom. So this is actually should be equal to 1. So the value I'm not going to see here. I'm not going to get the details of how we are getting this. So this will be 3, 4. This is solving the linear equations. So this is going to be 2, 3. If you do the elimination process of a matrix which will not alter the value of the determinant, you will see that the value of this is 1. And so the basis for G is 2, 3, 2, 5, 7, 1, 3, 4, and 0, 2, 3. We don't have much options here because it has to go down. So you can easily find out these values. The determinant value of a basis of this one would be this is actually going to be 2, 0, 0, 0, 5, 0, 0, 0, 7, and that is going to be 70. So the base element, basis for H is going to be D1, 2, 5, 7, D2, 1, 3, 4, and D3, 0, 2, 3. And when you multiply times D2 times D3, it should be 70. So how do you factorize this? So what are the possible values? See, once you factorize this one, 70 to 35, 5, 7. These are all primes, so we don't have much choice but to say that D1 is equal to 1, D2 is equal to 1, and D3 is equal to 70. So you can write it as 2 times 5 times 7. This is D1, this is D2, and this is D3, but will not satisfy the condition that D1 divides D2. Or you can say 1 times 10 times 7, or 7 times 10. That also will not work. Or you can say 1, 14, or 5 times 14. So none of this will work because these are primes. So the base element or basis for H is 2, 5, 7, 1, 3, 4, and 0, 140, 210. So this is the basis for this, and that satisfies our condition.